All right, everyone, welcome. Getting ready for your board exams and diving into Chapter 1 on gravitation? Well, you've come to the perfect spot. We're going to spend the next few minutes breaking down everything you need to know, the must-have concepts, the key formulas to totally ace this chapter.
It all kicked off with something super simple, an everyday thing, really. Picture this. Sir Isaac Newton sees an apple fall from a tree. But instead of just picking it up, he asks a simple question: why? And believe it or not, that single question sparked an idea so big, so revolutionary, it literally explains how the entire universe works.
So, here's our game plan. First, we'll get the big idea behind gravity. Then, we'll look at the rules of motion for the whole universe. Next up is your exam formula toolkit, followed by solving some real application questions. And we'll wrap it all up with a final knowledge checkup. Sound good? Let's go.
Okay, first things first, gravity. The big idea. We're going to go from a simple falling apple all the way to a universal force. Okay, so what is gravitation? This is probably the most fundamental definition you need to nail down. It's this universal force of attraction. And I mean universal. It's not just between two things here on Earth, but between any two objects in the entire universe. It's everywhere, and it affects absolutely everything. All right, next up, the universe's rules of motion. We're going to dig into Kepler's laws and centripetal force. You see, before Newton came up with his famous law, he had some serious groundwork laid for him by other brilliant minds. One of the biggest was Johannes Kepler.
So Kepler gave us 3 key laws about how planets move. The first one's pretty straightforward. Planets orbit in an ellipse, kind of like a stretched out circle, with the sun at one focus point. The second law is really cool. It says a planet sweeps out equal areas in equal amounts of time. What does that mean? Well, it means the planet actually speeds up when it's closer to the sun and slows down when it's further away. And the third law, this one was a game changer for Newton. It's a mathematical rule connecting how long a planet takes to orbit with how far away it is from the sun. It's that t squared over r cubed equals a constant, k. This was the piece of the puzzle Newton was looking for.
So what stops a planet from just, flying off into space in a straight line? It's this thing called centripetal force. The name literally means center-seeking. It's a force that's always pulling an object moving in a circle back towards the center.
And this is a perfect way to picture it. Think about swinging a stone on a string. The tension in that string is the centripetal force, pulling the stone inward. Well, it's the exact same idea with the moon and the Earth. Gravity is the invisible string that acts as the centripetal force, keeping the moon locked in its orbit. It's the same principle, just on a much, much grander scale.
Okay, moving on to your exam formula toolkit, these are the essential equations you absolutely must know for your boards.
All right, first up, and this one gets a star for a reason, this is the big one. F equals g times m1 m2 over d squared. This is Newton's universal law of gravitation. Seriously, if you memorize only one thing from this chapter, let it be this formula. It is the key to solving so many problems.
So let's break that formula down. What does it actually mean? First, the force, F, is directly proportional to the product of the masses. In simple terms, the more massive the objects, the stronger the gravitational pull. Makes sense, right? But the second part is what you really need to get. The force is inversely proportional to the square of the distance. This is huge. It means as things get further apart, the force doesn't just get weaker, it gets weaker fast. If you double the distance, the force is 4 times less. Triple the distance, it's 9 times less. That's the inverse square law, and it's a super important concept.
Next up, another starred formula, acceleration due to gravity, or little g. And please, please, don't mix this up with big G, the universal constant. They are totally different. Little g is the acceleration an object feels when it falls on a specific planet, like Earth. On our planet, it's about 9.8 meters per second squared. This formula lets you calculate it for any planet. And our last key formula is for escape velocity. This is pretty cool. It's the minimum speed something needs to just escape a planet's gravity completely, to just break free and never come back. Think of a rocket launching into deep space. For Earth, that speed is a staggering 11.2 kilometers per second.
Okay, now for the fun part, solving application-based questions. Let's put that toolkit to the test. All right, let's look at a typical problem you could see on your exam. An object takes 5 seconds to fall 5 meters on some planet. The question is, what's the value of g on that planet? Let's walk through it.
Okay, step 1 is always to figure out what you know. The object is just dropped, so its initial velocity, u, is 0. We know the distance, s, is 5 meters, and the time, t, is 5 seconds. Step 2. Pick the right tool from your toolkit. In this case, the second equation of motion, s equals ut plus half gt squared, is perfect. Step 3 is just plugging in the numbers. So 5 equals 0 times 5 plus 1/2 times g times 5 squared. And finally, step 4. Just solve for g. A little bit of algebra, and you'll find that g equals 0.4 meters per second squared. See, if you follow the steps, you'll nail it every time.
Now this is a super important distinction to make for your exams. Mass versus weight. They are not the same thing. Your mass is the amount of stuff you're made of. It's measured in kilograms, and it never, ever changes, no matter where you are in the universe. Your weight, on the other hand, is the force of gravity pulling on your mass. It's a force, so we measure it in newtons. Since gravity changes from place to place, your weight changes too. You'd weigh less on the moon, but your mass would be exactly the same. Get that difference clear in your head? It's a classic question.
Okay, time for a final knowledge checkup. Let's really use our brain power here. So, here's a thought provoker. If every object with mass attracts every other object, why aren't two things on a table, or even you and your friend, getting pulled towards each other right now?
Well, the wild thing is, the force is there. But because the masses of everyday objects are so tiny, the gravitational force between them is incredibly weak. It's so weak that other forces, like friction, just completely overwhelm it. So yeah, the pull exists. It's just too small for us to ever notice.
Okay, next question. We all know the Earth pulls the apple down, but does the apple also pull the Earth up? And if it does, why don't we see the Earth move? And the answer is yes, the force is equal. The apple pulls on the Earth just as hard as the Earth pulls on the apple. That's Newton's third law. For every action, there's an equal and opposite reaction. So why doesn't the Earth move? That's where Newton's second law comes in, F equals m. Because the Earth's mass is absolutely gigantic, that same amount of force results in an acceleration so tiny, it's basically zero. So the apple moves a lot, and the Earth, well, it doesn't really move at all.
So if you think about it, escape velocity is all about having enough speed to overcome gravity's pull and explore space. And that kind of makes you wonder, right? What are the other gravitational pulls in life, the challenges or doubts that knowledge can help us overcome? Something to think about. That's all for this chapter. Good luck with your exams. You got this.